Okay, let's get started with the discussion session of the cosmology session. Are there any remaining burning questions from the session that you would like to ask? Yes. We'll take maybe not more than 10 minutes for this part, and then.
Yeah, I have a very naive question. Like in the future detectors, we might detect like besides pop 1, 2 star, pop 3, and then a primordial black hole also will kind of come into play. But all these things are theoretical. All these population models are theoretical. And then my question is like, how do you disentangle this population from each other? Is it possible, or like, is there a way? Is there a study on that?
Or so the question is, how would you like to distinguish between PBH and astrophysical sources of all different population levels? So idea would be to go to the parameter space such as mass and distance where they are distinguishable. So at high redshift, one of the ways you could go and ask question is that the rate of merging is increasing or not. That's a distinguishing feature for primordial black holes to be observed and compared with the astrophysical background. However, there will be merger rates which will contribute to high redshift. So one of the proxy will be how fast they are growing, the rate at which the number of events we are observing at high redshift. The merger rate is growth, redshift evolution, and their mass distribution. So if there are sweet areas of masses where you do not expect black holes to form, that may be a place to look for. Among astrophysical models, it is going to be a challenging problem. As you have possibly heard yesterday, it is not going to be an easy scenario because there are several models, several channels which will give us, can give us similar predictions. We have to distinguish, but possibly one of the way forwards will be to get the mass spectrum as a function of redshift and see how they evolve.
Is that even clear for primordial black holes? Even if you're producing the primordial black holes as simpler physics, producing merging binaries out of them has a very complicated astrophysics there also, right?
Yes, that's a great point. So people have studied this option of primordial black holes in different scenarios, even in the presence of spatial clustering. And it's the very fact, let's just start with the point of teeth, the very fact that at the high redshift, higher you go, beyond redshift 10, 15, JWST observation is telling us star formation rate goes down. This is a unique feature. If I would like to go and now measure a rate which is not a decreasing function with redshift, but rather an increasing function of redshift, I can do that. Next comes the question of theoreticians to come up with a model which PBH can do that. That's very rare. But maybe someone, other experts can possibly talk about this, but it's challenging.
I think this is going back to Cole's point of what a model cannot do, right? For example, it's very hard for an astrophysical model to produce a black hole before the stars, but vice versa is not true. Even if you, right, even if you see a merger redshift that is merger rate that is going down at redshift, possibly the primordial black holes could do that still, because there's a delay between their formation binary.
So just very quickly on this point. So if supposing in a future detector like 3G, you saw a binary black hole merger at a redshift of 75 or 100, is that guaranteed it's a PBH?
If it is one object, no.
But
that's it's a rate, which is the evolution. So you need a few points to see how it evolves. One point will be.
Well, I mean, what mechanism is there to produce something at such a high redshift? That's the logic, right? I think you all also.
Yes, exactly. But I mean, high redshift is very unknown.
Probability, I agree, of producing astrophysical anything
rare, yeah,
at the kind of redshifts you mentioned is very low. So I would say yes, it is. I mean, I don't know whether it's a primordial black hole. It is definitely something exotic. Yeah. That would be clear. But this is where other observations come into the picture. I mean, once we have the 21 centimeter observations, we will know when the first stars formed. I mean, whether it's 18, 20 or what. And that may happen in the next few years if things go the way it's being planned. So hopefully that part will be settled very soon.
I mean, just to add to the can you hear me?
Yes, yes.
I mean, another possible way to, probably Shubhadeep discussed this briefly in his talk, that another possible way to distinguish between these primordial versus astrophysical scenarios is to, use our understanding of structure formation in some sense to see how these objects cluster, if it is different from how we expect astrophysical star, things that follow star formation to cluster. If we find that the clustering of these objects is very different from them, there is also some evidence for looking at scenarios beyond the traditional formation channels. Of course, whether PBHs are dark matter or not is again gives us a very specific kind of clustering to look at. But yeah, just deviation from these would be very exciting. Yeah.
Can I?
Yeah. Sorry. Yeah, you.
Just add one comment on the clustering of primordial black holes. I'm talking about this initial clustering of the primordial black holes. And in my talk, most people assume that initially primordial black holes are not clustered, so they are just randomly distributed. And this is a case when the primordial density perturbations, which creates primordial perturbations, obey Gaussian statistics. But if you include the non-Gaussianity of the primordial density perturbation, then it generally leads to the clustering of primordial black holes. And how the non-Gaussianity has infinite degrees of freedom. So you can have different types of varieties of clustering properties once you introduce the primordial non-Gaussianity. Yeah, that's. Yeah, you mean CMB constraint, right? Current. Yeah.
Okay, my question is to Archishman. Just a quick clarification. So when we combine dark siren measurements across events and so on, do we do it both by likelihood multiplication, assuming H naught is universal, and also allowing for H naught to be different? I forgot how we do it.
The same for all events, right? So the likelihood is H naught.
No, but I think I'm saying if you were to go with when things are evolving, why don't you do both and compare is what I'm asking. Is there a reason not to do it? Because
H naught is just one number, right? H naught is the slope.
Okay, so it's a Hubble. Okay, okay.
You can allow for other models. So
Okay.
if you the lambda CDM model, then you can allow for vary the other lambda.
Okay, that's fine. Yeah, got it. So, yeah, thank you.
Sorry, very quick comment on that. It is a good it's a good way to test for systematics if you try to fit for like different H naughts for different events. And this is exactly what we proposed when we tried to search for systematics in one of the papers that Archishman mentioned. And I think other people have also caught on to that. I saw a recent paper from the AEI group, which is also trying to do a similar thing. So yes, in the universe, H naught should be one number, but then if you want to test for systematics in the data, maybe testing if different events give us different H naught is a good idea.
I wanted to talk or ask about primordial black holes. So I very much like the idea that all of the dark matter is composed of primordial black holes in this sort of asteroid mass range. I wanted to ask, are there in the next few years going to be experiments or observations, studies of microlensing, small scale structure, things like that, that will place limits on these? Or is that window from 10 to the minus 15 solar masses to 10 to the minus 10 solar masses, is that window going to be open for a long time?
So I know one paper which investigated the possibility of probing such small mass black holes by using the so-called femtolensing. So femtolensing is lensing, but this source is a gamma ray burst, and the gamma ray has very short wavelength. So the Schwarzschild radius of the black hole is also small. This lensing causes this interference pattern, and yeah, wave optics. So So two gamma rays are like a, so when there's a lens in this, you have two light rays around the black hole. And so you observe like a two beams coming from the gamma rays, and this produces an interference pattern. So so if the primordial black holes exist and causes a femtolensing, so in the energy spectrum of the gamma ray burst, so even if the intrinsic spectrum is like a simple power law, you will see the modulation, like an oscillating pattern in this energy spectrum of the gamma ray photons. And yeah, the authors, I don't remember exactly, but that's a few years ago, but they like investigate some measuring these features by using gamma ray detectors. So, and I thought they were saying that it's possible, but I don't know. It's.
There were earlier some femtolensing constraints from GRBs, but it turned out they are not right because they approximated the source as a point source, while the extended emission actually could wash out these lensing features. So those constraints are removed. Yeah.
Okay, thank you.
Yeah, so I had a question regarding one particular slide where it was here. So in one particular slide, it was shown that the star formation rate is saturating at higher redshift, and to explain that, you can tweak the initial mass function in some way so that it increases. So if you tweak the initial mass function, I was wondering the number of supernova that would occur, and the supernova rates would also be different at those redshifts, and the number of white dwarfs getting formed, and also the number of neutron stars getting formed, the elemental abundances that you will find in everything would change, right? At that, is it such?
The IMF, various other things kind of get modified. It is just that even if they get modified, this is happening at really high redshifts. And as of now, we don't have a way to distinguish between a model where I have changed the IMF versus another model I have where I have kept the IMF, but somehow increased the star formation itself by switching off some feedback. As of now, I mean, given the data, in spite of JWST giving us such fantastic data, we don't have an obvious way of distinguishing between these models directly. It will happen, as I said, what happens is, suppose you, the degeneracy we are talking about is either you form lot of stars, or you vis-a-vis you form less number of stars but put them in appropriate masses so that you get the same luminosity. However, these two cases will differ in the history of the star formation, because if you put too many massive stars, they will be short-lived, versus if you put too many low mass stars, they will be long-lived. And that can be distinguished if you measure something like the stellar mass function, which is an integrated effect. So that is what people are trying, but the stellar mass function measurement is somewhat indirect, because some assumptions will go in calculating the stellar mass function, as opposed to luminosity, which is directly measurable. So this is the only trick, but otherwise, hopefully, with more and more data, some of these things will get sorted out.
Question to Tirth. So you said that the first question will be this high redshift evolution of the star formation rate. So I have seen like paper, I've attended a seminar, they are discussing like this bursty star formations. So I want to ask like which one fits better, like burst?
Yes. So what happens is, if you only talk about bursty versus continuous star formation, if you are only looking at the luminosity function data, it is like abundance versus luminosity. It is not very easy to distinguish between these two. So the rate is something like number of stars divided by star formation time scale. So there is a degeneracy. However, what will happen is, you have to use some other data, which is that if the star formation is bursty, at a given time, if you have all these dark matter halos, not all of them will be like forming stars very prominently. Let us assume that some of them have formed earlier, they have formed bursty star, there's a burst of star formation, and now currently they are quiescent. Whereas some halos which are there, but they have formed recently, they are still forming stars. So this is equivalent to something like a duty cycle in AGNs, not, it's the mapping is not one-to-one, but something like that. This will affect the clustering of the sources. Now, whether you have continuous versus bursty will, and given the same luminosity function, will affect the clustering. And I showed the plots, but did not get time to. One of these things was the time scale of star formation, which we can put constraints on that. And currently, yeah, it is towards the bursty side, but yeah.
So will it have any effect on this 21 centimeter global signal?
It will, okay. It will have, it is just that from going from JWST galaxies to neutral hydrogen, again brings in some new physics, which is you have to convert UV to ionizing radiation. And then you have to also say how much of that is escaping into the intergalactic medium, or how many Lyman alpha photons are there, how many extra photons are there. That will determine the shape. So you can always now tune these parameters again to bring it back. So it is non-trivial. It will probably get more sorted out if we have the power spectrum measurements of 21 centimeter, which SK is supposed to do. Because there you have different scales which are showing up.
Yeah, I see. Another thing you said that you can break the degeneracy between this IMF and the astrophysics by just stellar mass functions.
Yes, yes.
So do we have this stellar mass function measurement from, let's say, high redshift galaxies?
Yes, yes. So some of the JWST galaxies, people have measured stellar mass. So as I was responding to one of the questions. So problem with stellar mass function, stellar mass measurements is you most of the time you need accurate redshifts to do that. I mean, you need to model the star formation history basically, which means you have to model the full spectrum. I mean, not only just one UV part. So you need spectroscopic confirmation, which doesn't happen as often as photometric. And then there are some model assumptions which go in calculating the stellar mass. So it is not as direct as luminosity measurement, but there are stellar mass measurements in the literature. And for example, again, I didn't show that, but our models will fit those stellar mass measurements as well. I mean,
so let's take the last question on this part from Patrick, then we'll move on to
hello,
these,
I'm audible. Yeah, this is a question, related question to Tirthankar. So in the past, one would have expected that the interaction between galaxies would have played an important role in modifying the IMF. So is there, first part of the question is there evidence from JWST data that interacting galaxies, that interacting primordial galaxies were more in the past? And the second question is, could such interaction lead to a top-heavy IMF where you would produce such large stars whose relics would be 40 solar mass black holes that the LVK data is showing?
Yes. So I guess you're talking about like really galaxy mergers or something like that. Yeah. So no, there is no direct observational probe of, I mean, that we are seeing a galaxy where some merger has happened. No. So observationally at those high redshifts, we don't have a feel. I mean, we don't have an evidence for that. Of course, theoretically, we can calculate the merger rates and we know how they will be, but we haven't seen anything. Regarding the IMF, now this is a bit tricky. It depends on the model a bit. But one thing what can happen is, yeah, if you are merging two primordial galaxies where no metals have formed, maybe what you are saying will probably work. But what usually happens is the moment one round of star formation has happened, that will pollute the medium. So then it is metal enriched. Now, if that galaxy merges with another pristine galaxy, what will happen is that metals will get mixed with that, and then the IMF will go towards like less top heavy, will tend to move towards what we are seeing today. So yeah.
Okay, so maybe we'll start with now these. Do you want to say something about this discussion? Or? Yeah. So we'll introduce, Susmita will introduce those topics first, then we can go down. So Susmita, so the panelists have kind of come up with a bunch of questions that they find interesting, and we sorted them in some way. And we will start with Susmita, who would introduce this one broad topic of what is beyond Hubble.
Yeah, okay. So thanks, sorry not to be there, but looks like a wonderful discussion. So yeah, so I thought some of these things were already covered in the talks in the morning, but it'll be useful to sort of revisit some of those ideas. So of course, we know that gravitational wave, the standard siren method is a very promising way of getting the Hubble constant. But I think going forward, it is also interesting as our sample sizes get larger to start thinking about how can we go beyond just measuring the Hubble constant? What can we learn specifically given gravitational wave mergers are a direct measure of the luminosity distance? What can we learn about cosmology from these measurements, right? So, for example, of course, the underlying question is how, just like we do in looking at the distribution of galaxies, can we measure the clustering of BBH and BNS sources? It's true that currently the number density of these objects is about 2 orders of magnitude lower than the rarest number density of galaxy clusters. But while autocorrelation will be dominated by short noise, cross-correlation techniques will be very, very promising. But of course, here the question is that even with cross-correlations, how much can we push to small scales? And what are sort of the challenges of localization that will be brought about by localization? So I think that is one thing that remains to be completely worked out. The other thing is, assuming that we know Hubble, can we use these DL measurements directly to get the peculiar velocity distributions or the peculiar velocity fields? Or even in the case of BNS mergers, if we could, this is probably an astrophysical question, but can we use them to get sort of the kick distributions and so on? Right. So, and then thinking of cosmology beyond just measuring the cosmological parameters, I think it is interesting to think about how do the distribution and the rate of BNSs and BBHs agree with the overall star formation history of the universe. So these mergers are actually one of the few ways in galaxies we are sort of the majority of galaxies we are running out beyond redshift 2 now with JWST, of course, that's also there. But these are sort of probes of the universe between that redshift and an earlier redshift. And what can we learn about the star formation history of the universe at that time, the metallicity evolution, and how does it fold into sort of the mass distributions and so on. So these are sort of the larger cosmological questions that many of you have discussed, and we can discuss further. And because I have a bias also towards dark matter, and also think that is, of course, part of cosmology. So I think there is a lot of interesting things we can learn from the intersection of trying to understand the formation mechanisms of these binaries and the galaxy formation and structure formation, the connection between these two. For example, like how if we assume questions like whether we have dynamical formation channels versus isolated formation channels, and will have very important implications for what kind of galaxies that they form and what kind of underlying galaxy distribution that they trace or number density distribution that they trace. For example, if we could establish from lower redshift measurements what is the fraction of BBHs that form in globular clusters, for example, then we could also try to, from the gravitational wave side, for example, try to jointly constrain the evolution of globular cluster distributions over the history of the universe. Then, other than that, also, like if we can measure small scale clustering, we can start asking interesting questions about the dark matter distribution. And I think there are probes in the gravitational wave scenario where beyond, where we can actually start to prove this. For example, one very interesting thing that sort of, I've been working on with Avinash and Shashwat is this line of sight acceleration, which is a direct way of measuring the local acceleration, right? And can we use these to trace, for example, the local densities of dark matter, the local acceleration of created by the potential of the nearby environment, and how we can use this both at the single event level and also at a population level to talk about these things. Yeah, and then going beyond that, with things like LISA, where we'll be measuring the sort of white dwarf distributions. Can we map out, for example, the Milky Way potential distributions, which would again have these sort of implications for the dark matter distribution in the universe. So I'm just leaving these sort of open questions out there, and I know there are many speakers, so I'll stop here. There's a bunch of other questions that is there, and I think, of course, moving on, with dark matter, of course, gravitational lensing of gravitational waves is a really, really promising probe. With strong lensing, we've also do substructure detection. How does this work out in the gravitational wave scenario? And maybe the next speakers can talk a little bit more about what their specific interests are.
Okay, thank you, Susmita, for introducing these very interesting ideas. So maybe we will ask if any of the participants or panelists have something to say about the first set of topics before we go to the lensing, which will be introduced by Souvik also. Are there any comments or questions to make on these probes of galaxy connection, dark matter, peculiar velocities, and so on?
I think there's a question online.
Is it better now?
Yes, we close it.
Okay, now?
Hold the mic close.
Okay, now it's okay. Okay, sorry. So I want to make the point regarding the clustering aspect of binary black holes or neutron stars with galaxies. The problem because of the poor sky localization of not going to a much less than a square degree, it becomes difficult to measure or really isolate different channels. Gravitational bias parameter may look very different, but when you come to the measurement part, it becomes challenging. And possibly this is something one can explore at low redshift universe, where the corresponding, so just to some technical language, even for a given finite scale angular scale, the amount of scales you probe, if the object is nearby, is different. As a result, it helps you in some amount of clustering information. So long story short would be gravitational wave bias parameter is maybe a good way to go for a very low redshift universe, below 0.3, 0.4, to see some kind of differences between PBH and primordial black holes and astrophysical black holes. But beyond that, at least looks challenging to me in any sensitivity of detectors we have.
Any further questions or comments on this topic? Don't see any. So, let's move on. And Susmita introduced this idea of gravitational wave lensing. And this is what Souvik would like to say something about. He has a slide. I can just see that. Yeah, you can just see. Right. So he has a slide on this possibility of using lensing as a new tool for cosmology.
Audible? Okay. So I'll just put some context about this lensing so that the discussion can go on. So for the strong lensing of gravitational waves, the signature is it produces multiple images when it basically encounters galaxy clusters and galaxies. And these same copies of signal, which is scaled basically magnified or demagnified, and they will come to the detector at different times. So the strong lensing observables for our GW detectors are the time delays, which will be very accurately measured with millisecond precisions, and the distance ratio, which is basically the magnification ratio. So now these are the observables, and let's say we have a detection of gravitational lensed events. We have identified all the images, and first event have been detected. Now, can you do cosmology with it? So to do cosmology, we measure this time delay. So it depends on few things: lens redshift, source redshift, lens mass, and the relative position of the source and the lens. So the first problem is we do not see the BBH. And so we do not know the localization. And the sky localization is not so sufficient. We need the milliarc second precision to do this cosmology. And we do not see the lens, and also the lens rate should be unknown. So no cosmology without any complementary informations. So now if we want to do cosmology, for sure we don't know that particular event where exactly it is coming from and what is the particular lens. But what we do know is their populations, because we are detecting this GW BBHs. So we know their populations very well. So we know that the source is coming from that populations. And the lens populations we also know, because we know the dark matter simulations and these different halomas functions, and we know that these lenses are coming from these populations. So then we can do the cosmology. So this method actually just relying on that fact. And here what this plot shows what is the signature of this changing cosmological parameter on these time delay distributions. And the first plot is this, how this number of lens driven changes with respect to the cosmological parameters. And I'm not giving you the details. And also this second plot shows how this time delay distribution changes. And here you can see this the typical time delays for galaxies. It can go like minutes to like weeks to months. And for cluster, it can go like beyond years. And another thing is that we can also prove the dark matter, or prove this nature of the dark matter. And the main signature is that if the dark matter is not, let's say, cold dark matter, it's a warm dark matter, and what will happen, it suppresses the structure formation at these low mass scales. And that means the low mass lenses will be absent in the data. So there will be no lower time delay. So as the dark matter will be becoming more warmer, you can see there is a dip in this time delay distribution. So we can probe this nature of dark matter. Basically, we can measure the mass of this warm dark matter particle using this method. And also, as I said, that we need very high localization to do this cosmology. And there are possibility of localizing individual sources and lenses with this EM observation. So I'd like to first advertise this work by this Hanuksela et al. So what the idea is, basically with lensing, this is the only way to precisely localize the BBHs up to this milliarc second precision. So with this EM follow-up, you reconstruct the lens with the EM data, then predict the GW observable like this time delay ratios and these magnification ratios, whether they're consistent of this your lens reconstructions. Then you can do the actually sky localization. And then you are after sky localizing, the absolute scale of the time delay will give you the Hubble constant. So that is the idea. And then I'll just show our prospective constants. So yeah, this is the work done by Kostab Maiti. So he's presenting a poster. Please visit his poster for more details. And here I have this is just shows that predictions of our, like, depending on pessimistic and optimistic scenario of these merger rates and different lens populations. So these are the constants on this cosmology, and basically how H naught Hubble constants. And the right hand side plot shows how well actually we can measure this. Here I have considered that, let's consider our true universe is CDM, then how far basically we can constant the mass of this warm dark matter particle. And just to point out here that even with this pessimistic scenario, or pessimistic scenario, is the constants we are getting with this third generation detector is significantly better than the current existing constants. So, and also I have just mentioned about the strong lensing only here. There are other lensing features like wave optics features. It can be detectable, and you can probe the dark matter till what strong lensing cannot do. So I would like to hear from like experts that how this wave optics signature can help to go to very further on small scales. And also please feel free to add to this method section how well we can measure cosmological parameters.
Thank you, Souvik. Are there any comments on questions on this?
Thanks. Could you go back one? I just had a question about one of your plots. So in the first plot, this is showing the distribution of delay times. I guess the vertical line there is at 10
years. Yeah.
Years. And so what's the difference between the solid curves and the dashed curves?
Yeah. So we have the finite observation time period. So let's say one event come at this point, another event come outside the observation window. So we are not considering that in our analysis. So we are applying that selection cut to this timely distribution.
So then the distribution of events observable in 10 years of time.
So it's not a simple hard cut because dashed on are the intrinsic one, which will like lens all the lenses predicts, but solids are the observable in 10 years.
You have talked about the mass of the lens, which is an important factor, right? What about the density? Because that the density means lens means you are talking about the mostly the dark matter, right? What about the density? Even for a same mass, if we have the density of the dark matter is more, it will affect, right? The focusing and the time delays and all those things.
Yeah, so what matter in this density profile is not the, I'd say not this absolute scale, it's the density slope that matters actually, the lensing efficiency. And that's a question of this lens modeling uncertainties, and it's a fair point. But we have also like observed all like, lenses in EM galaxy, so we have to fit those lenses also. So that is the lens models we will choose for this prediction. So it should be calibrated with the observations.
Okay, so
here
you
we
are
assume
saying
the okay. So here we assume this SIS model, which is the singular isothermal sphere, pretty simple model.
So you're saying that the equation of state, basically the density, can be obtained from the from the delays and all those things, right?
So the thing we know that this dark matter, if you consider only halo, they are following this NFW profile, and that is a very good fit. Now on top of that, you need to put the baryons, and they follow. They are not this. Their slope is much steeper than the dark matter. So you have to consider all those facts. And with the only dark matter, the lensing efficiency will be very small. I mean, 10 to the power minus 6 or something. So we need the baryons to steepen the profile, and then the lensing efficiency will increase.
Okay. Okay, thanks.
So if the time delay is small, then I think it's not so hard to identify it as a lensed event. Because you don't have very good directional accuracy on the sky. I mean, if you get a signal and then 3 years later you get a signal from roughly the same area, how can you identify that as a lensed event rather than just as two separate events?
Yeah, so I think that's the lens identification, Ajith and Ankur.
That's a lensing or luck poster that Ankur presented yesterday. There's a poster about how well one could do that and keeping in the statistical uncertainties in doing this also. So it's difficult, but it can be done with for a fraction of events.
So, so that whether one can distinguish between these, it's not clear from this transparency, from this plot, but so the answer is you can. Okay.
Hello. I have a question regarding this time delay plot that you made for this lensing. So for getting the time delay, you need the model of the lens. Now for the BBH signals, we will detect for the gravitational waves. We really don't know the model of the lens, and the time delay heavily depends on the model. So there can be a degeneracy between the inferred parameters, so say H0 and omega m, and the models that we use. So, do you think there's a way to constrain those?
Yeah, so there is I mean, degeneracy. So if you don't assume the lens models, then, but the thing is that we have some knowledge about these things. We use that to break that degeneracy. So we will use the lens models, let's say SIS plus NFW, and we'll fit the EM data and then predict that time delay distribution. So that is the way to go. Yeah,
use a power law model or an SIE model. So the time delays can be very different regarding that. So the distribution can change.
Yeah, so when you have the data, you can do also the model selection. You choose your favorite model and see like which model is fitting the data. Also there are EM data, you have to fit everything.
For that, we need to identify all the images using GW, is it?
Okay, so this, we have only done for these 2 images. Of course, I mean, if you consider SIE, there will be 4 images, there are much more informations. Also this magnification ratios, so you have to, yeah, these are like, I have what I showed for SIS only. So yeah, you can utilize that informations. And identification is a separate problem. So I have not shown here. So there will be like contaminations also, false alarms. So we do model those, and also we can include those things.
Okay, last question on this from Aditya.
Hi. So you did discuss the effect of limited observation time on the time delay distribution, but in an ideal world, you'd want your 10 years of observation, but there'd also be duty cycles, and it will create some preferences to some time delay distribution that you observe. And your method of distinguishing warm dark matter from cold dark matter relied on it. So is there any effect of that systematics on inferring this cosmology?
Yeah, I mean, of course, there will be effect on for these duty cycles. And I think I'd refer to this Kostov's paper to account for these gaps in the observations.
There is a poster on this, accounting the gaps. This is by Kaustov, so you could take a look at that also. So let's move on. The next, Sriram, do you want to bring up this issue of primordial gravitational wave, possibility of observing some of the details of this one? Or
so
would you like to?
There were some questions about whether the PTA data indicate primordial gravitational waves. And I mean, I shared my view, and unfortunately, I will miss Bruce's talk tomorrow. Maybe you have some remarks. Oh, I'm done. I'm done. I would like to hear other views.
Yeah, so I wanted to talk specifically about the question is, do the PTA data point to primordial gravitational waves? So the PTA data in June 2023, 4 pulsar timing arrays, the Chinese pulsar timing array, the North American nanohertz timing array, the Chinese pulsar timing array, and then the European pulsar timing array, Indian pulsar timing array published papers. Of those, Nanograv claimed compelling evidence. PPTA claimed no evidence. EPTA, INPTA said that there was either, what did they say, marginal evidence or evidence, depending upon whether they consider the 25-year or the 10-year data set, and CPTA said some evidence. So none of that is at the 5 sigma level. And I believe that you can use that data to place upper limits. You can say, look, we can't have a gravitational wave background which is too large, or it would have been clearly observed by these instruments. But I think it's difficult, other than placing upper limits, to actually fit a model, because these detectors are trying to just determine 2 numbers right now, an amplitude and a slope. And even this cannot be done with any precision. So when you say, do PTA data point to primordial gravitational waves, I would say I'm skeptical that this is even a detection. It's not a detection yet. And do they point to something? At the moment, you can't even measure an amplitude and the slope with any precision. So I don't see how you can say that this points to anything. So I'm a bit pessimistic about this at the moment. Of course, the situation will be completely different in 10 years.
Point to gravitational waves. I mean, a stochastic background.
I'm skeptical about this. I think it's not yet at the 5 sigma level, and there are many things in the analysis which I believe could be done better, and will be done better in the future. But I think personally, it's much too soon to go off and compare hundreds of different cosmological primordial mechanisms to the data. I mean, it's fine if you want to do it. I wouldn't spend my time doing that yet.
Yeah, Sriram, in your talk, you showed that the gravitational waves were emitted even during the inflation, when the inflation was happening. My question is, how can you, general GR can, because the space-time itself is expanding. So can general, Einstein GR predict gravitational wave from them? Because primordial you are talking about, when the inflation is happening, the space-time itself is expanding, right? and you want to calculate the gravitational wave from emitted from there. The gravitational wave will have some non-trivial effects. So how are these done? Because I don't think Einstein gravity, because there will be effects from
Standard Einsteinian gravity, slow roll inflation, predicts some primary gravitational waves from the quantum vacuum.
But how good are these? Because inflations, your slopes are
not able to understand what do you mean by how good are these? There is a prediction. They will be generated from the vacuum. The same manner in which scalar perturbations are generated from the vacuum. They are no distinct.
Yeah, but question is it torsion free and all those things are still there?
Sorry?
Torsion free?
Yeah, you don't need. Even the simplest of scenarios will generate gravitational waves. What is their strength is not known.
Oh, no, my question is when the space-time itself is means expanding, is it okay to have Einstein GR?
I see no reason. I mean, you can have inflation driven by simple scalar fields.
Okay, but
even in Einstein GR.
Yeah, but how good are them? Is there any?
They're as good as they can be. There is no serious concern about that. Whether you trust those scalar fields, that's a different matter. But if you think the scalar fields exist, even simple models can generate inflation, and they will generate your density perturbations arise because of those fluctuations.
Okay.
And if the density perturbations arise, the same mechanism generates gravitational waves too, primary gravitational.
Okay.
Yeah. So, did you have a question on this?
Yeah. So I have a question that because now the debate is between in PTA whether the real signal that you have seen is between the foreground and background, but in future in ET&C era you will have BBH signals, astrophysical, and apart from that you will have cosmological background also. So can we ever resolve the foreground and background clearly, and whether always we'll be ending up with this ambiguity, because there are various sources, astrophysical like neutron star related processes, BBH, and also cosmological things. Can we ever do something better to say?
What is signal for the astrophysicist is foreground for the cosmologist. So, you have to have a clear understanding of your foregrounds, in order to see whether it is a cosmological signal. What is
that itself is uncertain, right? Because you don't know the foreground also well.
Okay, there are, yes, absolutely. There are many mechanisms to generate primordial gravitational waves. And I guess there are many mechanisms to generate astrophysical gravitational waves. And you need to see a pattern. And, there were talk about detecting in multiple frequencies. If you ask a cosmologist, they will predict, depending on the model at hand, they will predict a spectrum which probably runs across detectors. And maybe, you need to be judicious about the manner in which you remove foregrounds, etc., and, talk about primordial gravitational wave. Sudipta wants to say something.
I want to add a bit more on the astrophysics side. So yes, a great point. One possible way forward will be to a fact that astrophysical backgrounds will be coming from supermassive black holes, which are more point sources. So one will be more, so if there is no induced non-Gaussianity to start with in the cosmological background, you may expect a background to be more isotropic cosmologically in comparison to the astrophysical background. They may have a very different structure in the anisotropy as a function of frequency, we'll see. So that's one of the way forward to go, along with the spectrum.
So you're saying that the cosmological background will be more isotropic because they're coming from more farther, and astrophysical background will not.
Big galaxies, a few of them having binary black holes emitting signal in our detector lifetime, only a few of them. So they're like bright point sources, but finite number of them. But the cosmological background will maybe much more stochastic. And there's no preferred direction. It should be coming from everywhere. In absence of any, maybe like to add something on that, but that's one of the way forward.
I was going to make a comment about this too. If you look at the electromagnetic background radiation, there are certain windows in which you can see the cosmic microwave background radiation. From the ground, for example, 10 gigahertz is a good observing frequency. From space, Planck goes, I think, between 30 and 90, or I've forgotten what the frequency range is. And so, in the galaxy, for example, it's quite obscured at certain frequencies, but there are certain ranges of frequency where you can see the microwave background radiation. And I expect the situation is going to be the same for the gravitational wave background. There will be frequency ranges where it's obscured by the foreground of astrophysical sources. And there'll be other frequency ranges where hopefully it's clear of astrophysical sources and you can actually see further back in time. I think Jan Harms talked a bit about this when he gave his talk. I mean, at certain frequency ranges, we should be able to remove, for example, the effects of black hole mergers, neutron star mergers, and so on. And maybe with something like the Big Bang Explorer actually, or Big Bang Observatory actually get enough information to subtract away all of the foreground and see the background behind it. Maybe there's some other frequency ranges where it's more visible. I think the prospects are good. It's just a question of more data, more time, better instruments. I mean, 100 years from now, people will be presenting maps of the gravitational wave background with point sources identified and other sorts of things.
I just wish to add that that primordial background will be from multiple sources again.
Can I make a comment regarding this?
Yes.
I think
So,
in the past, well, I am online now. I might because of my throat. So we in the past we wrote some papers for this component separation sort of things. I think the primary, as Bruce mentioned, I think different sort of foregrounds can be estimated from different frequency bands. But I think the primary challenge would be the error in estimating the amplitudes of each of the components. That uncertainty in the foreground is a big problem for CMB measurements already, right? And similar problems will be there also for the stochastic gravitational wave background. I think which, even if we make a detection in, let's say, direct detection in.
Yeah, good point. So I think this is a good time to segue into the question that Teruaki posed. Is there something beyond omega that one could use to do the separation? Are you thinking of higher order statistics?
Especially the
so, Sanjit, so Teruaki want to say something about this impression? Yeah.
Yeah. So my question is very vague, and so my question has been partially, I think, addressed by Bruce and others. So, but my impression is, for instance, in the case of PTA observations, when this result came out, people say this can be explained by astrophysics or primordial signals by superposing the theoretical predictions with the observational data. So, my impression is that just by looking at the omega GW curve, then there are some degeneracies between astrophysical models and the primordial ones, and it's hard to say which one is correct. And so my question is, so other than omega GW, so that's a 2-point function of primordial, not primordial, 2-point function of gravitational waves. So higher order correlation functions or other observables can be useful to disentangle the astrophysical sources or primordial ones, cosmological ones. I don't have the clear answer, so if you have some.
I should have an answer.
This is not an answer, but I'm just throwing an idea out there. Maybe one thing that could help is what you pointed out in your slide regarding R of Z, which is, so the R of Z is connected to the omega GW, isn't it? So the two have to be compatible with each other. So maybe that could be one contributing factor when you try to, do you think that's a possibility?
But R of Z is not a measurable, right? What is measurable is the omega, and you can fit an R of Z that.
Yeah, no, from the resolvable sources, you get an R of Z, right? Isn't it? So that's my point, yeah.
I mean, there's lots of ways to tell the difference between a homogeneous stochastic background, for example, in point sources. So for example, in pulsar timing arrays, as you say, if the data actually is an observation and not just an upper limit, then you can explain this perfectly well with a few point sources. You could also explain it well with a homogeneous background. Both would fit perfectly well. It's only a question of getting enough signal to noise ratio. Once the data is good enough, then, for example, pulsars in the sky are more sensitive towards sources that lie behind them. than they are to sources that are on the opposite side of the sky. So if you have a point sources and you have enough good data, then you can distinguish point sources from homogeneous background. So it's certainly, I mean, non-Gaussianity might be another way to do this, but there's many different ways. It's just a question of having better data, more and better data.
In fact, one comment is that the papers we wrote, even using the same band, the LIGO band, you can actually do a component separation and separate out 2-3 different power laws. Basically, it is just get the Fisher matrix and invert it. But of course, you cannot go on doing it indefinitely. Like you cannot have 4 or 5 components. But then if the signal to noise ratio is already very poor, then you cannot do it.
It's purely a question of how much information you have, right? If you have a high enough signal to noise ratio measurement, then you can distinguish between many different possible alternative models. If your signal to noise ratio is low, then you have very little power to distinguish between them. So it's only a question of how much information you have.
Yeah.
Yeah, maybe just to add this, so this component different ways of component separation can depend on whether you want to do it in frequency domain, like that's being mentioned, some kind of shape. You can also look for anisotropy and kind of, if it is not too non-Gaussian, you can go for just power spectrum. And sometimes they are very point source, so power spectrum is not good for some non-Gaussian statistics because there are very few bright sources, so it's not a Gaussian sky. Other aspect which also shows up is the very fact that stochastic gravitational background may be dominated by signals which are short in length, much shorter than the observation time I am making. So there may be some popcorn-like or sporadic behavior in the time series data. One can explore this. We have shown that this can be another way. So spatial fluctuation, spectral shape, and temporal variation. These 3 are good in the high SNR limit to distinguish the signal. But, and maybe if there is an astrophysical component you want to detect, then you can cross-correlate with astrophysical catalogs like galaxies or so on.
When LIGO was in its initial stages, initial LIGO, and when the first advanced LIGO observing run began, or before it began, we were prepared to make detections at the signal to noise 8 or 9 or 10 level. And there's a huge amount of discussion and preparation for how could we make a confident detection at threshold of sensitivity. And then we got incredibly lucky. We got a signal with the signal to noise of 24, and everything that we'd worried about detection confidence and statistics and so on, we didn't have to worry about that anymore. Unfortunately, it looks like for stochastic backgrounds, like with the PTAs right now, we're not going to be in that situation. We're going to just crawl very gradually up to and over the threshold. And so the questions of confidence are unfortunately going to be the dominant ones. And everything about model constraining and so on, it all just comes down to signal to noise ratio. The amount of information is a function of that. And with little information, you just can't do inference. So it's not going to be something like the LIGO discoveries. It's going to be, unfortunately, I think, a very slow, steady crawl to progress.
But maybe I have one point to add to know your opinion. So that's true. What is your opinion on this around 4 nanohertz little bump, noise artifact, or something to look for? You know what I'm talking about.
There's no signal to noise ratio there. It's like
the highest one bin,
looking at a cup at the pattern of tea leaves. I'm sorry.
I know, but that's the only thing which is driving the entire measurement, more or less.
Look, you can look at a noisy data stream and see all kinds of things in there. It's just noise. So I'm sorry, it's premature to be looking at bumps and wiggles when you can't even measure 2 numbers with confidence.
I agree.
Okay, so we have another just about 5 minutes to wrap up the session. Should we go to the second part of this bullet points? this synergy between the 21 centimeter and gravitational waves. That's something, a rather new topic that Tirth has brought up. Would you like to?
So I guess the second point is something we have already discussed. So let's not worry about that. So the point I wanted to understand is that suppose hypothetically we have modeled the astrophysical aspects of the galaxy. So I know what is the IMF, what is the star formation rate, maybe the metallicity at a given redshift. What are the other inputs and how detailed they should be to go from there to predicting the actual event merger rates, basically? So for example, what would I need to model the delay time distribution? What are the kind of physics which I have to worry about at that stage? And so on. How do they depend on my IMF, maybe the high redshift density, and so on. So this is something I think will be a bottleneck in trying to cross-correlate these two. And any ideas or any thoughts or any work which has been done in this regard?
So basically, all the uncertainties that we discussed yesterday would play a role here. So have you thought of turning the table around? Because, probably cosmology is a little better understood than the astrophysics. So would it be possible to use this to inform the uncertainties in the binary astrophysics, which is already very uncertain?
Yes. In principle, yes. So the question now is, so you are saying these things can in principle be modeled and measured at high redshift, from astrophysics to merge?
No, other way around. If you see a 21 centimeter signal,
okay.
And we use it to inform the astrophysics. Yeah.
In principle, okay, yeah. Of course, that is the target. Here, we will assume that the cosmology is kind of known, and we will try to inform the astrophysics. But remember, as I was trying to make the point that there are various astrophysical processes which could be degenerate. But it is true that we will also have a wide variety of observations. So some of these astrophysics will probably get sorted out if SK, for example, behaves the way we expect them to do, or anyway, JWST is already happening. Some of the CMB observations, if they come about. So yes, so that is probably which will happen to some extent.
Yesterday's astrophysics session, we had this discussion of
basically
all formation channels are still game to explain the observed binary black holes in LIGO, etc. And it seems that it's very hard to distinguish between them as these models get more and more sophisticated. So any observational input to constrain these models would be very
So then the idea would be that suppose we fix the astrophysics part through other observations, and we see the binary black hole events, then we can probably use that to fix the astrophysics of
the binary black holes. I mean, that's my interest in my.
Yeah. No, probably that's probably. I mean, it's just that, I mean, at least in the 21 centimeter field, what we have seen is we are still dominated by systematics, and it will keep on happening for quite some time. So I don't know at what point we will be sure that we have nailed the astrophysics down. So yes, and that is the point I also wanted to, I was trying to make that SK and other things will come probably earlier than the 3G detector. So we'll probably have a lot of time to work on this part. So the suggestions we are making may be the way we will go finally.
Yeah. Can I add briefly?
Yes, Susmita, yes, yeah.
Yeah, so I think, this is a very interesting question, like what Tirth is saying, and also what Ajith, you're saying is how can the 21 centimeter measurements inform the gravitational wave binary distributions? And for example, some very obvious connections, like when star formation begins, what kind of implications does it have, for example, on the metallicity distribution of the stars that form in the early universe? So that will have very specific predictions for the black hole mass distributions. So maybe we can get predictions from these 21 centimeter measurements and try to turn those predictions into predictions for the black hole distribution and then try to see in the advanced detectors whether they're consistent or not, so those kind of questions are, I think, really interesting and not explored at all yet, I feel like.
Yeah, so there are ongoing efforts on this. Some papers are also coming out. So maybe you have to understand the scale in the problem. To some large scales, we will have some astrophysical informations, but at the small scale black holes, some of the unknowns will remain unknown, like metallicity dependent yield, metallicity dependent formation channels, so these are very difficult to manage from cosmological scale observations. So we may be able to make a map of cosmic star formation rate at some redshift. So metallicity information at those ratios, but how, because there's a stochasticity in metallicity and star formation rate from galaxy to galaxy.
Yes, but the rate evolution as a function of time is something that,
Yeah, that's the only thing, but the underlying scatter because of astrophysical uncertainty will remain, and hence that will drive the all sort of stuff we discussed yesterday on the astrophysical population synthesis side. So but it's a very good point. We can discuss this more.
Any information is
of
some use. Okay. Are there any final questions or comments before we break for lunch? If not, let's thank all the speakers and the panelists for this very interesting session.